Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do. Nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Geology is the scientific study of the Earth's physical structure, the materials that compose it, and the processes that have acted upon those materials across extremely long periods of time. When geologists describe geological processes, they are referring to mechanisms that operate through the interaction of matter and energy according to physical and chemical principles that can be observed, measured, and documented through empirical methods. These processes include the movement of tectonic plates, the deposition of sediment, the crystallization of minerals, the weathering of rock surfaces, and the gradual transformation of materials under conditions of varying temperature and pressure. Geologists approach these phenomena without assigning intention or purpose to them, understanding instead that they result from the natural operation of forces that have been present throughout the history of the planet and that continue to function in predictable ways according to the laws of physics and chemistry. The study of geology requires an understanding that rocks and minerals are not static objects frozen in time, but are instead components of dynamic systems that undergo continuous change at rates that vary depending on the specific conditions present in any given environment. A rock exposed at the Earth's surface is subject to weathering processes that gradually alter its mineral composition and physical structure. Water may infiltrate small fractures and expand when it freezes, causing mechanical breakdown of the material. Chemical reactions between atmospheric gases and mineral surfaces may dissolve certain components while leaving others intact. Biological activity, such as the growth of plant roots or the burrowing of organisms, may also contribute to the physical disruption of rock material. These processes occur simultaneously and continuously, though their effects become apparent only over extended periods of observation. Geologists recognize that the concept of geological time operates on scales that are vastly longer than those associated with human experience or even with recorded history. A single geological period may span millions of years, during which processes that appear imperceptible on human timescales produce cumulative effects of enormous magnitude. The formation of a mountain range, for example, may require tens of millions of years of tectonic activity during which crustal plates converge and compress, forcing layers of rock upward through mechanisms of folding and faulting. The erosion of that same mountain range may require an equally long period during which the elevated terrain is gradually worn down by the action of water, wind, and ice, with the eroded material being transported to lower elevations and deposited in sedimentary basins. Throughout this immense span of time, the processes themselves remain consistent in their fundamental operation, following the same physical principles that govern their behavior regardless of the specific geological context in which they occur. The Earth's surface is not a permanent or unchanging feature, but rather represents a temporary configuration of materials that are constantly being rearranged through the operation of geological processes. At any given moment, some regions of the Earth's surface are experiencing uplift, while others are subsiding. Some areas are accumulating sediment, while others are losing material through erosion. The balance between these competing processes determines the topography of any particular location at any particular time, but this balance is always subject to change as the forces acting upon the landscape shift in their relative intensity or spatial distribution. The appearance of stability that characterizes most landscapes on human timescales is simply an artifact of the extremely slow rates at which these processes typically operate, rather than an indication that the landscape is actually static or unchanging in any fundamental sense. Plate tectonics provides the framework through which geologists understand the large-scale movements of the Earth's lithosphere and the ways in which these movements shape the planet's surface features over geological time. The lithosphere, which includes both the crust and the uppermost portion of the mantle, is divided into a number of distinct plates that move relative to one another at rates typically measured in centimeters per year. These plates are not rigid in the sense that they never deform, but they are sufficiently coherent that they can be treated as discrete units for the purposes of understanding large-scale tectonic processes. The movement of these plates is driven by convective circulation within the underlying mantle, where differences in temperature and density cause material to rise in some locations and sink in others, creating patterns of flow that exert drag forces on the overlying lithosphere and cause the plates to move. Where two plates converge, the interaction between them depends on the nature of the crust that each plate carries. If both plates carry continental crust, which is relatively thick and buoyant, the collision between them may result in the formation of a mountain range as the crust is compressed and thickened. If one plate carries oceanic crust, which is thinner and denser than continental crust, that plate may be subducted beneath the other, descending into the mantle, where it is gradually heated and assimilated. Where two plates diverge, new crust is formed as mantle material rises to fill the gap, cools, and solidifies, creating new lithosphere that is gradually incorporated into the plates on either side of the divergent boundary. Where two plates move past one another without either convergence or divergence, the boundary between them is characterized by horizontal motion along a transform fault, which may produce earthquakes, but does not result in the creation or destruction of lithosphere. Sedimentation is the process by which particles of material are deposited in layers, typically in environments where the energy of the transporting medium, whether water, wind, or ice, decreases to the point that it can no longer maintain the particles in suspension or motion. This process operates continuously in a wide variety of settings, from the deep ocean floor to river floodplains, from desert dunes to glacial moraines, and from lake bottoms to coastal deltas. The particles that are deposited may be derived from the mechanical breakdown of pre-existing rocks, in which case they are classified as clastic sediments, or they may be the products of chemical precipitation or biological activity, in which case they are classified as chemical or biogenic sediments, respectively. Regardless of their origin, these particles settle out of the transporting medium in a manner that is governed by their size, shape, and density, as well as by the properties of the medium itself, such as its viscosity and velocity. Once deposited, sediments undergo a series of physical and chemical changes, collectively referred to as diagenesis, during which the loose aggregates of particles are gradually transformed into coherent rock. This transformation involves the expulsion of water from the pore spaces between particles, the precipitation of mineral cements that bind the particles together, and the compaction of the sediment under the weight of subsequently deposited material. These processes occur at relatively low temperatures and pressures compared to those associated with metamorphism, and they may require millions of years to complete, depending on the rate at which sediment accumulates and the depth to which it is buried. The resulting sedimentary rocks preserve a record of the conditions under which the original sediments were deposited, including information about the nature of the transporting medium, the energy of the depositional environment, and the types of organisms that were present at the time of deposition. Erosion is the process by which material is removed from the Earth's surface through the action of various agents, including flowing water, moving air, glacial ice, and gravity. This process operates continuously at rates that vary depending on factors such as climate, topography, vegetation cover, and the resistance of the underlying rock to weathering. In regions with high precipitation and steep slopes, erosion rates may be relatively rapid, measured in millimeters or centimeters per year, while in regions with low precipitation and gentle slopes, erosion rates may be extremely slow, measured in fractions of a millimeter per year. The material removed by erosion is transported away from its source and eventually deposited in a location where the energy of the transporting agent is insufficient to continue moving it, thus contributing to the process of sedimentation described previously. The action of flowing water is one of the most important agents of erosion in most terrestrial environments. Water flowing over the land surface exerts a shear stress on the underlying material, and if this stress exceeds the resistance of the material to detachment, particles will be entrained into the flow and transported downstream. The capacity of flowing water to transport sediment depends on its velocity and depth, both of which may vary considerably over time in response to changes in precipitation or snowmelt. During periods of high discharge, streams and rivers may transport large quantities of sediment, including particles of considerable size, while during periods of low discharge, transport rates may be minimal. Over time, the cumulative effect of this transport is to remove material from upland areas and deliver it to lowland areas, gradually reducing topographic relief and altering the configuration of the landscape. Weathering is the process by which rock material is broken down into smaller fragments or altered in its chemical composition through interaction with the atmosphere, hydrosphere, and biosphere. Mechanical weathering involves the physical disintegration of rock without change in its chemical composition, while chemical weathering involves the alteration of minerals through chemical reactions such as hydrolysis, oxidation, and dissolution. Both types of weathering operate simultaneously in most environments, though their relative importance may vary depending on factors such as climate, rock type, and the presence of vegetation. In cold climates, mechanical weathering processes such as freeze-thaw cycling may dominate, while in warm, humid climates, chemical weathering processes may be more significant. The rate at which weathering occurs depends on a variety of factors, including the surface area of the rock exposed to weathering agents, the mineral composition of the rock, the temperature and moisture conditions in the environment, and the length of time that the rock has been exposed at the surface. Some minerals are highly susceptible to chemical weathering and break down rapidly when exposed to water and atmospheric gases, while others are much more resistant and may persist at the surface for extended periods without significant alteration. Similarly, some rock types, such as those with abundant fractures or cleavage planes, may be particularly susceptible to mechanical weathering, while others, such as massive, unfractured rocks, may be more resistant. The products of weathering include both solid particles, which may be transported away by erosion, and dissolved ions, which may be carried away in solution by flowing water. Igneous rocks form through the cooling and solidification of molten material, either magma, which cools beneath the Earth's surface, or lava, which cools at the surface following volcanic eruption. The process of cooling allows atoms and molecules in the melt to arrange themselves into crystalline structures, forming minerals whose identity depends on the chemical composition of the melt and the conditions under which cooling occurs. If cooling is slow, as is typically the case for magma that solidifies deep within the crust, crystals have sufficient time to grow to relatively large sizes, resulting in a coarse-grained texture. If cooling is rapid, as is typically the case for lava that solidifies at the surface, crystals have less time to grow, resulting in a fine-grained texture, or, in some cases, a glassy texture in which no crystalline structure develops at all. The chemical composition of igneous rocks varies depending on the source of the magma and the processes that affect it during its ascent toward the surface. Magmas derived from the melting of mantle material tend to be relatively low in silica and high in iron and magnesium-producing rocks, classified as mafic or ultramafic. Magmas derived from the melting of crustal material or from the differentiation of mantle-derived magmas through processes such as fractional crystallization or crustal contamination tend to be higher in silica and lower in iron and magnesium-producing rocks classified as intermediate or felsic. These compositional variations have important implications for the physical properties of the magma, including its viscosity and gas content, which in turn affect the style of volcanic activity that may occur if the magma reaches the surface. Sedimentary rocks form through the lithification of sediments that have been deposited by water, wind, ice, or gravity. As described previously, this process involves the compaction of sediment under the weight of overlying material and the precipitation of mineral cements that bind the sediment particles together. The resulting rocks are typically composed of grains of various sizes and compositions, along with the cement that holds them together and any pore spaces that may remain unfilled. The characteristics of sedimentary rocks reflect the conditions under which the original sediments were deposited, and they often contain fossils or other features that provide evidence of past environments and life forms. Sedimentary rocks are particularly important for understanding Earth history because they preserve a sequential record of events that can be read by geologists through careful observation and analysis. Metamorphic rocks form through the transformation of pre-existing rocks, whether igneous, sedimentary, or other metamorphic rocks, in response to changes in temperature, pressure, or chemical environment. This transformation occurs in the solid state, meaning that the rock does not melt during metamorphism, although partial melting may occur at the highest grades of metamorphism. The minerals present in the original rock may become unstable under the new conditions and react to form new minerals that are stable at the higher temperature or pressure. The texture of the rock may also change, with minerals recrystallizing to form larger grains or developing preferred orientations in response to directed stress. The degree of metamorphism is typically described in terms of metamorphic grade, which ranges from low grade, where changes are relatively minor, to high grade, where the rock may be extensively recrystallized and bear little resemblance to its original state. The rock cycle is a conceptual framework used by geologists to describe the continuous transformation of Earth materials from one rock type to another through geological processes operating over time. According to this framework, igneous rocks, formed by the cooling of magma or lava, may be exposed at the Earth's surface, where they are subjected to weathering and erosion. The resulting sediments may be transported and deposited, eventually forming sedimentary rocks through lithification. These sedimentary rocks, if buried to sufficient depth, may be subjected to increased temperature and pressure, causing them to metamorphose into metamorphic rocks. Metamorphic rocks, if buried even deeper or subjected to even higher temperatures, may partially or completely melt, forming magma that may eventually cool to form new igneous rocks. This cycle has no definite beginning or end, and any given rock may follow various pathways through the cycle, depending on the specific geological processes to which it is subjected. The role of pressure and temperature in determining the mineral composition and structure of rocks is fundamental to understanding geological processes. Minerals are crystalline solids characterized by specific chemical compositions and ordered atomic structures, and each mineral is stable only within a particular range of temperature and pressure conditions. When a rock is subjected to conditions outside the stability range of its constituent minerals, those minerals may react to form new minerals that are stable under the new conditions. This process is the basis of metamorphism, and it results in systematic changes in rock composition and texture that can be used to infer the conditions to which the rock has been subjected. The specific minerals present in a metamorphic rock therefore provide information about the temperature and pressure conditions that existed during metamorphism, allowing geologists to reconstruct the thermal and tectonic history of a region. The layering observed in many sedimentary rocks results from variations in the characteristics of sediment deposited over time, reflecting changes in the energy of the depositional environment, the supply of sediment, or the composition of the material being deposited. Each layer or stratum represents a discrete episode of deposition, and the boundaries between layers, known as bedding planes, mark interruptions in deposition or changes in depositional conditions. This sequence of layers in a sedimentary succession provides a chronological record of events, with older layers typically located beneath younger layers, a principle known as the law of superposition. This principle allows geologists to determine the relative ages of rock layers and to correlate layers from different locations, building up a regional or even global picture of geological history. The preservation of information in rock layers does not involve any intentional recording or storage mechanism, but simply results from the fact that the physical and chemical characteristics of sediments reflect the conditions under which they were deposited. A layer of coarse-grained sandstone, for example, indicates deposition in a relatively high-energy environment, such as a beach or river channel, where strong currents were capable of transporting and depositing large particles. A layer of fine-grained shale, in contrast, indicates deposition in a low-energy environment, such as a lake bottom or deep marine setting, where only small particles could remain in suspension long enough to be transported to the site of deposition. By examining the characteristics of successive layers, geologists can reconstruct the sequence of environments that existed at a particular location over time, even though the original environments may have disappeared long ago. Gravity is a fundamental force that influences all geological processes, from the large-scale movement of tectonic plates to the small-scale transport of individual sediment particles. The weight of overlying rock layers causes compaction of underlying sediments, driving the process of lithification and contributing to the development of metamorphic textures at greater depths. Gravity also drives the downslope movement of material through processes such as mass wasting, in which soil, rock, and debris move downhill under the influence of gravity without the aid of a transporting medium such as water or ice. This movement may be rapid, as in the case of landslides or rockfalls, or extremely slow, as in the case of soil creep, where individual particles move downslope at rates measured in millimeters per year. Over time, the cumulative effect of gravity-driven processes is to transport material from higher elevations to lower elevations, contributing to the overall process of erosion and the gradual reduction of topographic relief. The concept that geological change rarely requires sudden events is central to the principle of uniformitarianism, which holds that the geological processes operating today are the same as those that have operated throughout Earth history, and that these processes are generally gradual and continuous rather than sudden or catastrophic. While it is true that certain geological events, such as volcanic eruptions, earthquakes, and meteorite impacts, occur suddenly and may produce dramatic local effects, the large-scale features of the Earth's surface are primarily the result of slow, steady processes operating over vast periods of time. Mountain ranges are built not by single catastrophic events, but by the cumulative effect of countless small increments of uplift occurring over millions of years. Similarly, canyons are carved not by sudden floods, but by the gradual erosion of rock by flowing water over millions of years. The recognition that gradual processes can produce large-scale geological features represents one of the fundamental insights of modern geology. The Earth's interior plays a critical role in regulating processes that occur at the surface, even though the interior is not directly accessible to observation. Heat flow from the interior drives the convective circulation in the mantle that powers plate tectonics, and it also drives volcanic activity and the creation of new crust at divergent plate boundaries. The distribution of heat within the interior is controlled by a combination of factors, including the decay of radioactive isotopes, which generates heat, and the conduction and convection of heat toward the surface, which removes heat from the interior. The balance between heat production and heat loss determines the thermal state of the interior, which in turn influences the vigor of mantle convection and the rate at which tectonic processes operate. Changes in this balance over geological time may result in changes in the style or intensity of tectonic activity, affecting the configuration of continents and ocean basins, and the pattern of mountain building and basin formation at the surface. Slow movement can produce large geological outcomes because geological processes operate over extremely long periods of time, allowing small incremental changes to accumulate into substantial effects. A tectonic plate moving at a rate of a few centimeters per year may seem to be moving imperceptibly on human timescales, but over a period of millions of years, this rate of movement can result in the closure of ocean basins, the collision of continents, and the formation of major mountain ranges. Similarly, erosion proceeding at a rate of a fraction of a millimeter per year may seem insignificant, but over millions of years, this slow, steady process can remove kilometers of material from the surface, exposing rocks that were once deeply buried and completely altering the topography of a region. The key to understanding how slow processes produce large effects is to appreciate the immense amount of time available for these processes to operate, and to recognize that even very small rates, when sustained over geological timescales, can result in changes of enormous magnitude. The repetition of natural forces over time creates stable landforms because certain configurations of Earth materials are more resistant to erosion or more efficiently maintained by ongoing processes than others. A river, for example, tends to develop a channel with a particular cross-sectional shape and gradient that represents a balance between the rate at which the river transports sediment and the rate at which sediment is supplied to the river from its drainage basin. Once this equilibrium configuration is achieved, the river channel tends to maintain its form even though the processes of erosion and deposition continue to operate. Similarly, a beach tends to develop a particular profile that represents a balance between the energy of incoming waves and the size and supply of sediment available on the beach. While the beach may undergo short-term fluctuations in response to storms or seasonal variations in wave climate, it tends to return to its equilibrium profile over time as long as the controlling factors remain constant. These equilibrium configurations are not static in the sense that no change is occurring, but they are stable in the sense that the system tends to return to the same configuration after disturbances. Geological systems tend toward equilibrium because physical and chemical processes naturally adjust to minimize energy differences and to balance inputs and outputs of matter and energy. A landscape that is elevated above its surroundings has gravitational potential energy, and erosion represents the conversion of this potential energy into kinetic energy as material moves downslope. As erosion proceeds and elevation decreases, the rate of erosion typically decreases as well, because the energy available to drive erosion is reduced. Eventually, the landscape may approach a condition in which the rate of erosion is approximately balanced by the rate at which tectonic processes supply new material to be eroded, resulting in a relatively stable configuration that may persist for extended periods. This condition, sometimes referred to as dynamic equilibrium, does not mean that all processes have ceased, but rather that the rates of competing processes are balanced so that no net change occurs over time. Landscapes feel stable despite constant change because the rates at which geological processes typically operate are far too slow to be perceived directly by human observers. A mountain range may appear to be a permanent and unchanging feature of the landscape, but in reality, it is being continuously eroded by weathering and erosion, and the material removed from it is being transported to lower elevations and deposited in sedimentary basins. Over millions of years, the mountain range will be gradually worn down, and the sedimentary basins will be filled with the eroded material, resulting in a fundamental alteration of the landscape. From the perspective of a human lifetime, or even the span of recorded human history, these changes are imperceptible, creating the impression that the landscape is stable and unchanging. In reality, however, the landscape is constantly in flux, responding to the ongoing operation of geological processes that have been active throughout Earth history and that will continue to be active far into the future. Geological calm, in the sense of the absence of dramatic or catastrophic events, is simply a reflection of the fact that most geological processes operate at low rates under most conditions. While it is true that certain geological events, such as earthquakes, volcanic eruptions, and landslides, can occur suddenly and produce locally intense effects, these events are relatively rare in any given location, and the intervals between them are typically much longer than the duration of the events themselves. For the vast majority of the time, geological processes operate in a gradual and continuous manner, with changes occurring so slowly that they are not directly observable on human timescales. This does not mean that nothing is happening, but rather that the activity is occurring at a low rate, with the cumulative effects becoming apparent only over extended periods of time. The concept of low-rate physical activity as the norm in geological systems is important for understanding the nature of geological change and for interpreting the rock record. Many of the features observed in rocks, such as layering, folding, faulting, and metamorphic textures, are the products of slow, steady processes operating over millions of years, rather than the products of sudden, catastrophic events. A fold in a rock layer, for example, may appear to represent a dramatic deformation of the rock, but in reality, it was likely formed by slow, continuous compression over millions of years, with the rock deforming in a ductile manner at a rate too slow to produce fracturing. Similarly, a metamorphic texture may appear to represent intense conditions of temperature and pressure, but these conditions were likely achieved gradually as the rock was buried over millions of years and then maintained for millions of years more while metamorphism proceeded. Understanding the timescales over which geological processes operate is therefore essential for correctly interpreting the features observed in rocks and for reconstructing the geological history of a region. The formation of minerals within rocks is governed by the chemical composition of the material and the conditions of temperature and pressure to which it is subjected. Each mineral has a specific chemical formula and a specific crystal structure, and these characteristics determine the range of conditions under which the mineral is stable. When a rock is subjected to conditions under which its existing minerals are no longer stable, chemical reactions occur that transform the unstable minerals into new minerals that are stable under the new conditions. These reactions may involve the addition or removal of chemical components, the reorganization of atoms into new crystal structures, or both. The rate at which these reactions proceed depends on factors such as temperature, pressure, the presence of fluids, and the diffusion rates of atoms within the rock, with higher temperatures and the presence of fluids generally promoting faster reaction rates. The study of mineral stability and the reactions that occur between minerals provides geologists with a powerful tool for understanding the conditions that existed within the Earth's crust and mantle at various times and in various locations. By identifying the minerals present in a rock and determining their compositions and textures, geologists can infer the temperature and pressure conditions under which the rock formed or was metamorphosed, as well as the composition of any fluids that may have been present during these processes. This information can then be used to reconstruct the thermal and tectonic history of a region, providing insights into processes such as mountain building, basin formation, and the generation and emplacement of magma. The concept that rocks are dynamic systems rather than static objects is fundamental to modern geological thinking. A rock may appear to be an inert, unchanging object when observed on human timescales, but when viewed from the perspective of geological time, it is revealed to be part of a continuously evolving system in which materials are constantly being transformed from one state to another through the operation of physical and chemical processes. A sedimentary rock deposited on the floor of an ancient ocean may be buried by subsequent deposition, subjected to increasing temperature and pressure as burial continues, metamorphosed as its minerals react to form new assemblages, stable at higher temperatures and pressures, and eventually uplifted and exposed at the Earth's surface, where it may be weathered and eroded, with the resulting sediments being transported to a new site of deposition and the cycle beginning again. Throughout this process, the material is never truly at rest, but is always responding to the changing conditions to which it is subjected, moving through different states in the rock cycle as the forces acting upon it vary over time. The timescales over which geological processes operate can be difficult for non-geologists to grasp because they are so far removed from everyday human experience. A process that operates at a rate of 1 millimeter per year, for example, may seem trivially slow, but over 1 million years, this rate corresponds to a total displacement of 1 kilometer, which is a geologically significant amount. Similarly, a process that operates at a rate of 1 centimeter per year may seem slow, but over 10 million years, this rate corresponds to a displacement of 100 kilometers, which is sufficient to close a small ocean basin or to build a major mountain range. The ability to think in terms of such long timescales and to appreciate the cumulative effects of slow processes is one of the key skills that geologists develop through their training and experience. Erosion proceeds through a combination of processes that work together to break down rock material and transport it away from its source. Weathering prepares the rock by breaking it into smaller fragments or by altering its mineral composition, making it more susceptible to physical removal. Once the material has been loosened or disaggregated, it can be entrained by flowing water, moving air, glacial ice, or gravity, and transported to a new location. The distance that material is transported depends on factors such as the energy of the transporting agent, the size and density of the particles, and the characteristics of the terrain over which the material is moving. Coarse particles tend to be transported only short distances before being deposited, while fine particles may be transported over much longer distances, sometimes hundreds or thousands of kilometers from their source. The deposition of sediment occurs when the energy of the transporting medium decreases to the point that it can no longer support the weight of the particles being carried. This typically occurs when flowing water slows down as it enters a lake or ocean, when wind velocity decreases, or when glacial ice melts. The particles settle out of the transporting medium and accumulate on the surface, forming layers of sediment that may eventually be lithified into sedimentary rock. The characteristics of the sediment, including the size, shape, and composition of the particles, as well as the structures formed during deposition, such as ripple marks or cross-bedding, provide information about the conditions under which deposition occurred, including the velocity and direction of the transporting medium and the water depth and energy level of the depositional environment. The accumulation of sediment over time results in the formation of sedimentary basins, which are regions where subsidence, either due to tectonic processes or to the weight of the accumulating sediment itself allows for the continued deposition and preservation of thick sequences of sedimentary rocks. These basins may persist for tens or hundreds of millions of years, during which time thousands or even tens of thousands of meters of sediment may accumulate. The sedimentary sequences preserved in these basins provide a detailed record of the geological history of the region, including information about changes in climate, sea level, tectonic activity, and the evolution of life. By studying these sequences, geologists can reconstruct the environmental conditions that existed at various times in the past and can trace the evolution of the Earth's surface over geological time. The concept of geological time is essential for understanding the processes that have shaped the Earth and for interpreting the rock record. Geological time is divided into a hierarchical series of units, including eons, eras, periods, epochs, and ages, each of which represents a specific interval of time characterized by particular geological events or conditions. The boundaries between these units are typically defined by major changes in the rock record, such as mass extinctions, the appearance of new fossil groups, or significant changes in the types of rocks being deposited. The absolute ages of these boundaries are determined through radiometric dating, which uses the decay of radioactive isotopes to determine the age of rocks with a high degree of precision. This combination of relative dating based on the stratigraphic sequence of rocks and absolute dating based on radiometric methods allows geologists to construct a detailed chronology of Earth history extending back over 4.5 billion years. The rate at which tectonic processes operate can vary considerably depending on the specific process and the geological setting in which it is occurring. The spreading rate at mid-ocean ridges, for example, varies from about 1 centimeter per year at slow-spreading ridges to more than 10 centimeters per year at fast-spreading ridges. The rate of convergence at subduction zones is similarly variable, ranging from a few centimeters per year to more than 10 centimeters per year. These variations in tectonic rates have important implications for the style and intensity of geological activity associated with plate boundaries, including the frequency and magnitude of earthquakes, the rate of volcanic activity, and the rate at which mountain building occurs. Despite these variations, however, all tectonic processes operate on timescales that are extremely long from a human perspective. with significant changes in the configuration of continents and ocean basins requiring tens to hundreds of millions of years. The study of sedimentary structures provides important information about the conditions under which sediments were deposited and about the nature of the transporting and depositional processes involved. Ripple marks, for example, are small-scale undulations formed on sediment surfaces by the action of flowing water or wind, and their shape and orientation provide information about the direction and velocity of the current. Crossbedding is a sedimentary structure formed when sediment is deposited on inclined surfaces, such as the lee sides of dunes or ripples, and it provides information about the direction of sediment transport and the geometry of the depositional environment. Graded bedding is a structure in which particle size decreases upward within a single layer, and it typically forms when a sediment-laden current slows down, depositing coarser particles first and finer particles later. These and other sedimentary structures are preserved in the rock record and can be used by geologists to reconstruct ancient environments and to interpret the processes that were active at the time of deposition. The chemical weathering of minerals occurs when they react with substances present in the environment, such as water, oxygen, carbon dioxide, and organic acids. These reactions alter the mineral structure and composition, often producing new minerals that are more stable under surface conditions. For example, feldspars, which are common minerals in igneous rocks, weather to form clay minerals through a series of chemical reactions involving the addition of water and the removal of alkali and alkaline earth elements. This process of chemical weathering is important not only because it breaks down rock and prepares material for erosion, but also because it plays a role in regulating the chemistry of natural waters and in controlling the availability of nutrients for biological systems. The products of chemical weathering, including dissolved ions and clay minerals, are transported by water and eventually deposited in sedimentary basins, where they may be incorporated into sedimentary rocks. The transformation of sediment into sedimentary rock through the process of diagenesis involves a number of changes that occur as sediment is buried and subjected to increased temperature and pressure. One of the most important of these changes is compaction, which occurs as the weight of overlying sediment squeezes water out of the pore spaces between particles and causes the particles to pack more closely together. This process reduces the porosity and permeability of the sediment and increases its density and strength. Another important diagenetic process is sedimentation, which occurs when minerals precipitate from pore waters and bind the sediment particles together. Common cementing minerals include calcite, quartz, and various iron oxides and hydroxides. The type of cement present in a sedimentary rock can provide information about the chemistry of the pore waters and the conditions under which diagenesis occurred. The concept of metamorphic grade refers to the intensity of metamorphism to which a rock has been subjected, with low-grade metamorphism involving relatively modest changes in mineral assemblage and texture, and high-grade metamorphism involving more extensive recrystallization and the formation of minerals that are stable only at high temperatures and pressures. The transition from one metamorphic grade to another is typically gradual rather than abrupt, with mineral assemblages changing progressively as temperature and pressure increase. Different rock types respond differently to metamorphism depending on their initial mineral composition and on the specific pressure-temperature path followed during metamorphism. A shale, for example, may be transformed first into slate, then into schist, and finally into gneiss. As metamorphic grade increases, with each transition being marked by changes in mineral assemblage and texture. The forces that drive plate tectonics are ultimately related to the thermal structure of the Earth's interior and to the convective circulation that occurs in the mantle as heat is transported from the deep interior toward the surface. The mantle behaves as a very viscous fluid over geological timescales, and convection occurs because hot material is less dense than cold material and tends to rise, while cold material is denser and tends to sink. This creates large-scale patterns of circulation in which hot material rises beneath mid-ocean ridges, spreads laterally beneath the lithospheric plates, cools as it moves, and eventually sinks back into the mantle at subduction zones. The drag exerted by this convective flow on the base of the lithospheric plates is one of the primary forces responsible for driving plate motion, along with the gravitational forces associated with the elevation of mid-ocean ridges and the negative buoyancy of subducting slabs. The interaction between tectonic processes and surface processes creates a complex feedback system in which changes in the elevation and configuration of the Earth's surface influence the rates and patterns of erosion and sedimentation, which in turn influence the distribution of mass at the surface and the isostatic response of the lithosphere. When a mountain range is uplifted by tectonic processes, for example, the increased elevation leads to increased rates of erosion as gravity drives material downslope and as precipitation patterns change in response to the presence of the elevated terrain. The removal of material from the mountains by erosion reduces the load on the lithosphere, causing it to rise isostatically, which may partially compensate for the material that has been removed and may maintain high elevations even as erosion continues. This interplay between tectonic uplift and erosional removal is one of the factors that determines the long-term evolution of mountain ranges and the persistence of elevated topography. The formation of igneous rocks through the cooling of magma or lava is a process that involves the nucleation and growth of crystals from a liquid phase. As the temperature of the melt decreases, atoms and molecules lose kinetic energy and begin to arrange themselves into ordered crystalline structures, forming the nuclei of mineral grains. These nuclei then grow as additional atoms and molecules attach to them with the rate of growth depending on factors such as the degree of undercooling, the viscosity of the melt, and the availability of the chemical components needed to form the growing crystals. If cooling is slow, crystals have time to grow to relatively large sizes, and the resulting rock has a coarse-grained texture. If cooling is rapid, many small crystals form, and the rock has a fine-grained texture. If cooling is extremely rapid, there may not be sufficient time for crystals to form at all, and the melt solidifies as a glass. The chemical composition of magma evolves as crystallization proceeds because different minerals crystallize at different temperatures. And because the minerals that crystallize may have compositions that differ from the composition of the melt as a whole. When a mineral crystallizes and is removed from the melt either by settling to the bottom of a magma chamber or by adhering to the walls of the chamber, the composition of the remaining melt changes. This process, known as fractional crystallization, can result in a single parent magma producing a series of different rock types as crystallization proceeds and the composition of the residual melt evolves. The sequence of minerals that crystallize from a cooling magma is predictable based on the composition of the magma and the temperature and pressure conditions. And it can be described using diagrams known as phase diagrams that show the stability fields of different minerals as functions of temperature, pressure, and composition. The concept of isostasy refers to the principle that the Earth's crust floats on the denser mantle below in a manner analogous to the way that icebergs float in water. With the elevation of the surface, depending on the thickness and density of the crust. Where the crust is thick, as beneath mountain ranges, the surface stands at high elevations, but the base of the crust extends deep into the mantle to compensate for the mass of the elevated terrain. Where the crust is thin, as beneath ocean basins, the surface stands at low elevations, and the base of the crust is relatively shallow. This isostatic balance is maintained by the flow of mantle material in response to changes in the load on the surface. If material is added to the surface, such as through the accumulation of sediment or the emplacement of a volcanic edifice, the crust subsides to accommodate the additional load. If material is removed from the surface, such as through erosion, the crust rises to compensate for the reduced load. The study of fossils preserved in sedimentary rocks provides important information about the history of life on Earth and about the environmental conditions that existed at the time the fossils were deposited. Fossils can be used to determine the relative ages of rocks through the principle of faunal succession, which states that different fossil assemblages occur in rocks of different ages, and that the sequence of fossil assemblages is consistent from one location to another. This allows geologists to correlate rocks from different locations and to construct a global chronology of Earth history based on the evolutionary progression of life forms. Fossils also provide information about ancient environments, as different organisms are adapted to different environmental conditions, and their presence in the rock record indicates the types of environments that existed at the time of deposition. The process of fossilization involves the preservation of organic remains or traces of organisms in the rock record. This can occur through a variety of mechanisms, including the replacement of original organic material by minerals, the preservation of original hard parts, such as shells or bones, or the formation of molds or casts in sediment. Fossilization is a relatively rare occurrence because it requires that the organism be rapidly buried after death to protect it from decay and scavenging, and that the surrounding sediment undergo lithification to form rock before the remains are destroyed. As a result, the fossil record is biased toward organisms with hard parts and toward environments where rapid burial is common, such as marine or lake settings. Despite these limitations, the fossil record provides an invaluable window into the history of life and the evolution of organisms over geological time. The gradual nature of most geological processes means that the Earth's surface is in a constant state of flux, with materials being continuously cycled through different reservoirs and different states. The material that forms a mountain today may once have been part of the deep ocean floor, deposited as sediment, buried, metamorphosed, uplifted, and exposed by erosion. That same material may eventually be eroded again, transported to a new site of deposition, and incorporated into new sedimentary rocks, continuing this cycle indefinitely. This view of the Earth as a dynamic, evolving system in which materials are constantly being transformed and recycled stands in contrast to the static view of the Earth that prevailed in earlier times, when the planet was thought to be essentially unchanging except for occasional catastrophic events. The recognition that the Earth is ancient and that geological processes have operated over immense periods of time was one of the key insights that led to the development of modern geology. Early estimates of the age of the Earth, based on biblical chronology, suggested an age of only a few thousand years, which was far too short to accommodate the slow, gradual processes that geologists were beginning to recognize as important. The development of radiometric dating in the early 20th century provided a means of determining the absolute ages of rocks with unprecedented precision. And these dates confirmed that the Earth is approximately 4.5 billion years old, providing ample time for slow geological processes to produce the large-scale features observed at the Earth's surface. The transfer of heat from the Earth's interior to the surface occurs primarily through two mechanisms: conduction and convection. Conduction involves the transfer of heat through solid material by the vibration and collision of atoms. And it is the dominant mechanism of heat transfer in the lithosphere, where temperatures are relatively low and the material is sufficiently rigid that large-scale flow does not occur. Convection involves the transfer of heat by the movement of material. and it is the dominant mechanism of heat transfer in the mantle where temperatures are high enough that the material can flow over geological timescales. The heat that reaches the Earth's surface is ultimately radiated into space, maintaining a long-term balance between the heat generated in the interior by radioactive decay and the heat lost from the surface. The concept of uniformitarianism, which states that the processes operating today are the same as those that have operated throughout Earth history, does not mean that the rates or intensities of these processes have remained constant over time. Tectonic processes, for example, may have operated more vigorously in the early history of the Earth when the interior was hotter and convective circulation in the mantle was more vigorous. Similarly, rates of erosion and sedimentation may have varied over time in response to changes in climate, vegetation cover, and sea level. What uniformitarianism does assert is that the fundamental physical and chemical principles governing geological processes have not changed over time, and that by studying the processes operating today, geologists can gain insights into the processes that operated in the past. The observation that landscapes tend toward equilibrium configurations does not mean that all landscapes are currently at equilibrium, or that they will necessarily remain at equilibrium in the future. External factors such as climate change, tectonic activity, or changes in sea level can disrupt existing equilibrium states and cause landscapes to adjust to new conditions. A river that is in equilibrium with its current discharge and sediment load, for example, may begin to erode its channel if discharge increases due to changes in precipitation patterns. Or it may begin to deposit sediment if sediment supply increases due to increased erosion in its drainage basin. These adjustments occur over time scales that depend on the magnitude of the change and the response time of the system. But eventually, the system may approach a new equilibrium state that reflects the changed conditions. The layering of sedimentary rocks is one of the most fundamental features of the rock record, and it provides the basis for the stratigraphic subdivision of Earth history into a hierarchical series of units. Each layer represents a period of deposition, and the characteristics of the layer, including its thickness, composition, fossil content, and sedimentary structures, provide information about the conditions that existed during that period. Changes in these characteristics from one layer to the next reflect changes in environmental conditions over time, such as changes in water depth, current strength, sediment supply, or biological productivity. By carefully documenting the sequence of layers and the changes that occur between them, geologists can reconstruct the history of environmental change in a region and can correlate this history with events occurring elsewhere to build up a comprehensive picture of global geological history. The transformation of rocks through metamorphism is driven by the tendency of mineral assemblages to adjust to changes in temperature and pressure in such a way as to minimize the free energy of the system. When a rock is subjected to conditions under which its existing minerals are not stable, the minerals react to form new minerals that are stable under the new conditions, releasing or absorbing heat in the process and changing the overall energy state of the rock. The specific reactions that occur depend on the initial mineral composition of the rock, the temperature and pressure conditions to which it is subjected, and the availability of fluids that may facilitate chemical reactions by providing a medium for the transport of ions. The study of metamorphic reactions and the mineral assemblages that result from them provides geologists with a powerful tool for determining the pressure-temperature history of rocks and for understanding the tectonic processes that have affected them. The circulation of fluids through rocks plays an important role in many geological processes, including metamorphism or formation and the alteration of rock properties. These fluids, which may consist primarily of water, but may also contain dissolved ions, gases, and organic compounds, move through the pore spaces and fractures in rocks in response to gradients in pressure, temperature, and chemical potential. As fluids move through rocks, they may dissolve certain minerals and precipitate others, changing the mineral composition of the rock and transporting chemical components from one location to another the permeability of rocks, which refers to their ability to transmit fluids, varies widely depending on factors such as porosity, the degree of interconnection between pore spaces, and the presence of fractures or other pathways for fluid flow. Rocks with high permeability allow fluids to move relatively freely, while rocks with low permeability impede fluid movement and may effectively isolate certain regions from fluid circulation. The presence of fluids during metamorphism can significantly enhance the rate at which metamorphic reactions proceed, because fluids facilitate the transport of ions between mineral grains and provide a medium in which chemical reactions can occur more readily than they would in the solid state alone. Fluids may be derived from the dehydration of hydrous minerals as temperature increases during metamorphism, or they may infiltrate from external sources, moving through the rock along fractures or grain boundaries. The composition of these fluids can vary depending on their source and on the reactions that occur as they move through the rock, and the presence of certain components in the fluid, such as carbon dioxide or various dissolved salts, can influence the stability of minerals and the types of reactions that occur. The study of fluid inclusions, which are small pockets of fluid trapped within mineral grains during crystal growth, provides information about the composition and properties of fluids that were present during metamorphism or during the crystallization of igneous rocks. The formation of ore deposits, which are concentrations of economically valuable minerals, often involves the circulation of hydrothermal fluids through rocks. These fluids, which are typically heated, by proximity to magmatic intrusions, or by circulation to great depths, where temperatures are elevated, can dissolve metals and other elements from the rocks through which they pass, and can transport these dissolved components over considerable distances. When the fluids encounter conditions that cause the dissolved components to precipitate, such as a change in temperature, pressure, or chemical environment, or minerals may be deposited in fractures, pore spaces, or as replacements of pre-existing minerals. The resulting or deposits may be highly localized and may contain concentrations of metals that are orders of magnitude higher than the average crustal abundance of those metals, making them economically viable sources of mineral resources. The gradual subsidence of sedimentary basins occurs in response to a variety of mechanisms, including the cooling and contraction of lithosphere that has been heated and extended by tectonic processes. The loading of the lithosphere by the weight of accumulating sediment, and the flexural response of the lithosphere to loads such as mountain ranges or volcanic edifices. As subsidence proceeds and sediment accumulates, the base of the sedimentary sequence is buried to progressively greater depths, where it is subjected to increasing temperature and pressure. This burial may eventually result in diagenesis and lithification of the sediment, transforming it into sedimentary rock, and if burial continues to sufficient depths, metamorphism may occur, transforming the sedimentary rock into metamorphic rock. The rate at which subsidence occurs varies depending on the mechanism driving it and on the tectonic setting, but in most cases, subsidence is a slow process that continues over millions of years, allowing thick sequences of sediment to accumulate The study of the thermal history of rocks involves determining the temperatures to which rocks have been subjected over time and the rates at which they have been heated or cooled. This information can be obtained through a variety of methods, including the study of metamorphic mineral assemblages, which provide constraints on peak temperatures and pressures, and the analysis of isotopic systems that record cooling histories as rocks are exhumed and brought toward the surface. Different isotopic systems close at different temperatures, meaning that they cease to exchange atoms with their surroundings and begin to preserve a record of time at different points during the cooling process. By analyzing multiple isotopic systems in the same rock, geologists can reconstruct the cooling history in detail, determining not only the peak temperature reached, but also the rate at which the rock cooled and the time at which it passed through various temperature thresholds. The exhumation of rocks from depth to the surface involves the removal of overlying material by erosion, which allows deeper rocks to rise toward the surface. In response to isostatic adjustment, as rocks are exhumed, they pass through progressively lower temperature and pressure conditions, and if exhumation is sufficiently rapid, the rocks may preserve mineral assemblages that formed at depth and that are not in equilibrium with surface conditions. The rate of exhumation can be determined by combining information about the cooling history of the rocks with information about the thermal gradient in the crust, which describes how temperature changes with depth. Exhumation rates vary widely depending on the tectonic setting, ranging from fractions of a millimeter per year in tectonically quiescent regions to several millimeters or even centimeters per year in regions of active mountain building or rapid erosion. The interaction between climate and tectonics influences the evolution of landscapes through its effects on erosion rates and patterns in regions with high precipitation. Erosion rates tend to be higher because flowing water is the primary agent of erosion in most terrestrial environments, and the amount of water available controls the capacity for erosion. Climate also affects the types of weathering processes that are most active, with chemical weathering being more important in warm, humid climates, and mechanical weathering being more important in cold climates or in arid regions with large temperature fluctuations. Vegetation cover, which is controlled in part by climate, also influences erosion rates by protecting the soil surface from raindrop impact and by binding soil particles together with root systems. Changes in climate over geological time, such as those associated with glacial interglacial cycles, can therefore result in changes in erosion rates and in the redistribution of sediment across the landscape. The formation of glaciers occurs when snow accumulates faster than it melts over a period of years, allowing it to compact into ice and eventually to flow under its own weight. Glaciers are powerful agents of erosion because ice is capable of entraining and transporting rock fragments of all sizes, from fine clay particles to large boulders, and because the movement of ice over bedrock can erode the underlying surface through processes of abrasion and plucking. And now, as everything slowly settles into stillness, as the earth continues its quiet processes, there is nowhere you need to go, nothing more to observe, nothing to analyze. This moment is complete. You are at rest. Let the silence of deep time surround you. Let the darkness feel stable and steady. Let your thoughts slow like erosion over long ages. May your body become heavy like settled layers of stone. May your breath move slowly and evenly like heat traveling through the crust. May your mind drift without effort as continents drift without urgency, as the earth continues its gradual change. You may drift just as gently into sleep, and when morning comes, may you rise calm, balanced, and quiet, carrying a soft sense of deep time. Good night and rest within the steady earth.